Hello, welcome to section 1.3 of the M132 course, Introduction to Linear Algebra at AOU. In this section, we will look at different things that can be done with matrices. In other words, what type of operations can be done with matrices. And the title of this section is Matrices and Matrix Operations. This is part of chapter 1 of the book that we're using. To begin with, we start by defining a matrix. What is a matrix? And for this reason, we can say an m by n matrix A is a rectangular array. In other words, is a rectangular list of numbers of n real numbers arranged in m horizontal rows and n vertical columns. The matrix A has size m by n. The elements in the row I and column j of the matrix A is written as Aij, where I represents the number of the position of the element in the ith row, and j is the position of the element in the jth column. For example, if A is as follows, as shown here, A has the size of 4 by 4 matrix. 4 by 4, it has 4 rows and 4 columns. And these are the corresponding elements or the list of numbers that are inside the two brackets here that represent the matrix. And the element A13, which is in the first row, third column, is 3. Also, the element 34, which is in the third row, fourth column, is 4. In general, a matrix A is noted as follows. Matrix A here is an m by n matrix. It has first element A11, A12, A13, etc. A1n, A21, AM1 to AMN. A horizontal set of elements is called a row. These elements represented horizontally are rows. These elements are represented in a column. The first subscript represents the row number, and the second subscript represents the column number. And again, within the matrix notation area, we notice here that A23 is an element that is located in the second row, third column, at the intersection of the second row, third column. AMN is a matrix that has m rows and n columns. It has the dimensions m by n, written m times n, but pronounced m by n. Type of matrices. The different types of matrices that we will encounter in this course are: number 1 type is a square matrix. A square matrix is a matrix that has equal number of rows and columns. For example, this one here is a 3 by 3 matrix. It has 3 rows and 3 columns. We can see that the main diagonal of the matrix is the diagonal that's running from left to right. This is called the main diagonal. The second type is an upper triangular matrix. An upper triangular matrix happens to have elements different than 0 on the top right hand side or right hand side, and zeros on the bottom left hand side. And how we determine that? The position of the element Aij is equal to 0 every time I is greater than j. Here the element is 2, 1, 2 is greater than 1, therefore it must be 0. A31, 3 is greater than 1, therefore the element is 0. A32, 3 is greater than 2, therefore the element must be 0. Here the element is 3, it shouldn't be a 0. It can be if it happens to be by a certain calculation. But in order to be an upper triangular matrix, it has to satisfy the way it is shown here. A third type is a lower triangular matrix, which is the opposite of this. Aij equal to 0 every time I is less than j. Here we notice that the location of the element is 1, 2, 2 is greater than 1, therefore the element is 0, etc. A fourth type is a diagonal matrix. A diagonal matrix has only elements along the main diagonal and zeros everywhere. An identity matrix is a matrix that has ones along the main diagonal, as you can see here, and zeros everywhere else. This is I2. It means that it is a 2 by 2 identity matrix. I3 is a 3 by 3 identity matrix. The sixth type of matrix is a zero matrix. This is a 2 by 2 zero matrix. It has zero elements everywhere. This one is a 2 by 3 zero matrix. It has 2 rows of zeros and three columns of zeros. And a row matrix is a matrix that has row elements only. This is a 1 by 3 matrix. A column matrix is a 3 by 1. This is a 3 by 1 matrix. It can be n by 1 matrix. Here it can be 1 by n matrix. And these are the types of matrices that we will encounter in this course. Now, how we start doing matrix operations. We start off by doing addition or subtraction of matrices. Therefore, as a general rule, in order to add or subtract two matrices, the two matrices must be of the same size, and when we add them or subtract them, we add or subtract the corresponding elements in each of the matrix. So the sum of a 2m by n matrix is an m by n matrix called C. Okay, it's defined by adding the corresponding elements. Aij is added to Bij. Example, we have a 3 by 3 matrix A and a 3 by 3 matrix B. To add the two matrices, first, these two can be added because they have the same size. Second, with the way we add them together is we add the corresponding elements. 1 plus minus 2 is minus 1, 2 plus 1 is 3, 3 plus 3 is 6, etc. In order to subtract them, the same deal happens. We subtract the corresponding elements. 1 minus 2 becomes a plus 3. 2 minus 1 is 1. 3 minus 3 is 0, etc. B minus A is done in a similar way. What are the properties of matrix addition? First of all, A plus B is equal to B plus A, provided the matrix operation can be done. In other words, here we are applying the commutative property in addition. Here, the second one is A plus B plus C is equal to A plus B plus C. This is the associative property. This is adding any matrix to the zero matrix will produce the A matrix. A minus A will give us is equal to minus A plus A is equal to the zero matrix. Another thing we can do with matrices is called the matrix scalar multiplication. In other words, we can multiply a scalar value, a real number, by a matrix. In order to do that, we multiply each element of the matrix by the scalar elements. For example, we have here a matrix A, for example, which is a 3 by 3 that is multiplied by a scalar value, a real number, which is minus 3. In order to obtain the results, we multiply each element of this matrix by minus 3. For example, looking at the first row here, it was obtained by multiplying minus 3 times minus 1, minus 3 times 2, and minus 3 times 0 to obtain respectively 3, minus 6, 0, etc. Another example, multiplying 1/2 times this 2 by 2 matrix will produce this 2 by 2 matrix. What are the properties of a scalar multiplication of a matrix? If R and S are two scalar values that belong to R, if we have R plus S times A, this is as if we can do R times A plus S times A. If R is multiplied times the sum of two matrices, we can distribute the scalar multiplication as shown. It becomes RA plus RB. Or R times S times A is equal to RS times A. We can multiply the scalar values together. And of course, 1 times A is equal to A. Matrix multiplication. In order to multiply two matrices, we need to apply this concept. And the concept that we need to apply is the dot or scalar or inner product of two n vectors. How this is accomplished is as follows. If we have a matrix U, which is a row matrix, and a vector, a column vector V, the product of the two together is obtained by multiplying the corresponding elements. In other words, u1 times v1 plus u2 times v2 plus u3 times v3, etc. till we end un times vn. If we add these all these numbers together, these products together, we obtain the scalar multiplication of the two vectors, and this becomes a number. Example, if we have here this is what, a 1 by 4 row matrix and a 4 by 1 vector matrix here. If we multiply these two together, 2 times 4 plus minus 3 times 3 plus 4 times minus 1 plus 3 times 5, it gives us 10. Therefore, if we want to multiply two matrices in general, if we have a matrix A that has a size m by p and a matrix B that has a size p by n, then the product matrix, which is C, obtained by multiplying A times B, is an m by n matrix. As you can see, matrix A is m by p and the B is p by n. Notice the p here is equal to the p here. Therefore, in order to multiply two matrices, these two numbers have to be the same, and the output or the matrix that is obtained has the size of the outer values here, m by n. Okay, in other words, this is in column and matrix representation of the multiplication. How we do that? We take this row, multiply it by this row to obtain the various values of the C's. Okay, therefore, to summarize this, the rule is two matrices A and B can be multiplied if the number of columns of A, which is the left matrix, is equal to the number of rows of the B, which is the right matrix. The elements in the ith row and the jth column of the product matrix AB is obtained by adding up the product of corresponding elements of the ith row of A and jth column of B. Example, if we have two 2 by 2 matrices A and B, the product matrix AB becomes a 2 by 2 matrix. And how is this obtained? Is by multiplying, taking the first row of A, multiply it times the first column. So 2 times 4 plus 1 times 2 is obtained here. Then 2 times 6 times 1 minus 1 is here, give us the element here. Then we start with the second row. 3 times 4 plus 0 times 2 is here. Then we take the second row times the second column. 3 times 6 plus 0 times minus 1 will give us this value here. When we add all these up, we obtain the 2 by 2 matrix, which is the product A times B, becomes 10, 11, 12, and 18. Another example for matrix multiplication is if the matrix A and B are both of them a 3 by 3 matrix. Then the matrix C, which is the product of the two, is obtained as follows. We have matrix A on the left, matrix B on the right, and in order to multiply the two together, we start off by taking the first row here, we multiply it times the first column here, then the first row by the second column here, then the first row by the third column. Once we do that, we obtain these 3 elements here, 1, 2, 3. Then we take the second row and we repeat the process. Then we take the third row and we repeat the process to obtain the last 3 elements and rows here. We add them up to obtain matrix C as shown here, which is a 3 by 3 matrix again. So this is how we do the matrix multiplication. Two matrices can also be multiplied if they are this different size, but we have to be careful here. As mentioned before, the number of columns of the left matrix has to equal the number of rows on the right hand matrix. In this case, we have matrix A, which is a 2 by 3, and B is a 3 by 2. Therefore, they can be added together, they can be multiplied, I should say, together, and the output is a 2 by 2 matrix as shown here. So we take the first row times the first column, the first row times the second column, the second row times the first column here, and the second row times the second column here. Now, if A is a 3 by 3 matrix, which is a square matrix, then we can raise it to a power. So the rule for raising a matrix to a power is for the matrix to be a square matrix. Any other matrix that is not a square matrix cannot be raised to a power. And how we can raise the matrix to a power is we place two copies of the matrices next to each other, and we perform the multiplication as if we're doing for two different matrices. In other words, we set them next to each other and we start off by applying the multiplication of two matrices, and this will give us the matrix multiplied to power 2. If we need to power 3, we repeat it again with the third matrix, and so forth. What are the properties of the matrix multiplication? If we have A times B times C is equal to AB times C, this is the associative property. A times B plus C is equal to AB plus AC. In other words, we have to be careful here. We're multiplying matrix A from the left side. We multiply B and C from the left side by the matrix A. Same thing here is happening. A plus B times C. We multiply C by from the right hand side, so it becomes AC plus BC. Therefore, we notice here that in multiplication, matrix multiplication, the order is important. In other words, if I say A times B, it does not necessarily means that it's equal to B times A. Therefore, A times B does not necessarily mean equal to B times A. And the fourth item here, AI, where I is the identity, is equal to A, and IA is equal to A, and A to the power n is equal to A times A n times. Matrix multiplication, problem 2. If A is a 2 by 2 matrix, 1 1 0 1, find all matrices B such that AB is equal to B to A. AB is equal to BA. How we do that? We take any matrix that is 2 by 2 made up of scalar values x, y, z, w, where x, y, z, w belong to R. If AB is equal to BA, then what we have to do is do the multiplication as seen below. AB equal to BA, we set the two matrices next to each other the way they are represented here. Then we do the multiplication to obtain x plus z, y plus w, z, w. On this side, x plus y, z, z plus w. In order for two matrices to be equal, first of all, they must be the same size, in which case they are, and the corresponding elements have to be equal. So if we present the equality of the corresponding elements, we obtain a system of 4 equations and 4 unknowns. If we summarize this, we obtain z is equal to 0, x equal to w. Therefore, as a summary, z is equal to 0, x equal to w equal to t, and w and y is equal to r. So in general, any matrix that has this form here, tr 0 t, where t and r belongs to r, can produce this equality, AB is equal to BA. Any other one does not make this equality hold. The transpose of a matrix is obtained by changing the row of the matrix into a column. So interchange the rows, obtained by interchange the rows and the columns of A. Example, if A is a 2 by 2 matrix that has 3 4 minus 2 5, we take this in order to generate the transpose of the matrix. We take this row, we change it to a column. 3 4 becomes 3 4, minus 2 5, the second row becomes the second column. For example, B with a 3 minus 2 5 is a row matrix, becomes a column matrix. This is a 4 by 4 matrix. The transpose becomes like this, stays the same size, 4 by 4. What are the properties of the transpose of a matrix? If A transpose is raised to a transpose, then in other words we apply the transpose twice to a matrix, we obtain the original matrix. They cancel each other. A plus B transpose is equal to A transpose plus B transpose. This we have to remember, is very important. A times B transpose is equal to B transpose times A transpose. Notice the order here. And RA raised to the transpose equal to R times A transpose. What are some of the properties of a symmetric matrix? A square matrix A is said to be symmetric is A transpose equal to A. So therefore, whenever A transpose is equal to A, the matrix A is called a symmetric matrix. This is an example, matrix C and matrix C transpose. If you compare the two together, you notice that C is equal to C transpose, therefore C is a symmetric matrix. Some of the properties, other properties, if A is an n by n matrix, then A plus A transpose and A times A transpose are both symmetric. So how we prove that? If we consider the first one, A plus A transpose transpose equal to A transpose plus A transpose transpose, this remains the same and this becomes A. A transpose plus A, if we commute the two together, because the addition of matrices is commutative, then this is equal to A plus A transpose. So it satisfies this condition here. The second one, A times A transpose, A times A transpose transpose is equal to A transpose transpose times A, which is equal to A transpose transpose is A times A transpose, which means that these two together are symmetric. Another problem here, if A and B are symmetric matrices, then AB plus BA is also symmetric. Let's see that. AB plus BA transpose is equal to AB plus BA. When we do the transpose on the product of these two, it becomes B transpose times A plus A transpose times B, as seen before. So B transpose A transpose, because A and B are symmetric, then B transpose is B, A transpose is A, plus A transpose becomes A and B transpose becomes B. And since BA plus AB is matrix operation is commutative, the addition is commutative, then BA plus AB is equal to AB plus BA. Symmetric and skew symmetric matrices. We've talked about symmetric matrices. Now we turn to skew symmetric matrices. By definition, a matrix is skew symmetric if A transpose is equal to minus A. A transpose is equal to minus A. Therefore, the transpose of the matrix is equal to negative values of all the elements of the matrix. So if we have example, the matrix C as shown below and C transpose as shown below it, then if you notice all the elements are equal, they are the same size, the two matrices, then and CT is equal to minus C. Therefore, C is said to be a skew symmetric matrix. What are some of the properties of a skew symmetric matrix? If A is an n by n matrix, then A minus AT is skew symmetric. Let's see that. A minus AT, A transpose is equal to A transpose minus A transpose transpose. It's equal to A transpose minus A transpose transpose minus A. This is equal to, if we change the position, this is equal to minus A minus AT, which is the skew symmetric value of this one. Another example, if A and B are skew symmetric, then AB plus BA is symmetric. AB plus BA transpose is equal to AB transpose plus BA transpose, which is equal to B transpose times A transpose plus A transpose times B transpose. But since A and B are skew symmetric, B transpose is equal to minus B, A transpose is equal to minus A transpose is equal to minus A, and B transpose is equal to minus B. We substitute the values here. Once we multiply them together, minus times minus is plus, so this becomes plus BA plus AB. And since the matrix operation addition is commutative, BA plus AB is equal to AB plus BA, which means that AB plus BA is skew symmetric and is symmetric. Okay, this ends section 1.3. I hope you find it easy. If you have any questions, please feel free to discuss it with your tutor. This should end the session.